On Thursday, March the 15th, 2018, 11 miles west of downtown Miami, a dashcam captured this disturbing footage. A cutting-edge bridge had collapsed midway through construction onto Southwest 8th Street. 10 people were injured, but tragically 6 were killed. Although it fell in less than a second, the pioneering structure had been failing for weeks. So why did it collapse that day? Hey, I'm Tom, and you're watching Why Stuff Fails. To help explain what caused this disaster, I'm being joined by an authority on engineering failures, Dr. Steve Ressler. Steve had a distinguished career in the US Army Corps of Engineers before teaching the next generation at the West Point Military Academy. So Steve, thank you again for joining me. You know, you'll have seen the dashcam footage. What was your reaction when the news started to come out afterwards?
Well, I mean, certainly my first reaction was horror. It was clear that there were workers on the bridge working at the time.
Right.
And so there was no doubt that when the collapse occurred that there were going to be serious injuries at absolute best, but probably fatalities. Of course, we know now that there were 6 fatalities as a consequence.
The NTSB immediately launched an investigation, right? Guess they interview everybody, witnesses, victims, engineers. How do they then work out what was actually wrong with the bridge?
The investigators from NTSB know just how to zero in on the point of failure, so they will have carefully inspected the wreckage, documented it very carefully with photographs, probably took some material samples to be tested in the laboratory, and then they did their own assessment of the structure.
Right. Is that through looking at the designs and analyzing those?
That's exactly right.
Was the complex design an issue? You know, when you look at the original plans, you might say this looks like it's going to be a cable stay suspension bridge, like the Sunshine Skyway, the Queens Ferry Crossing, a whole bunch of other bridges around the world. But that's not the case, right?
This is actually kind of a complex hybrid structural system designed as a 2-span concrete bridge. But at the most fundamental level, this structure was a truss. You see trusses all the time in the world around you. A truss is, by definition, a structural framework,
right,
consisting of relatively slender members that are interconnected at joints and that are arranged geometrically as a series of interconnected triangles. Now, of course, the FIU bridge was a truss of a different sort. And as we saw in your diagram, your drawing, and in this model, yes, you can see the general arrangement of interconnected triangles. The triangles are geometrically rather odd and asymmetrical, but they are interconnected triangles. And that's really what makes this a truss.
So although it looked like a suspension bridge, that span is a self-supporting structure with no help from above or below other than the ends resting on the piers, I guess.
Technically, the pylon and the stays were designed to provide a very small degree of additional load-carrying capacity with respect to extreme loads. There's no structural reason why those diagonals had to be in that orientation. It really just looks cleaner if those particular diagonals are a direct extension of the stays.
So the asymmetry here is entirely to fit with the cosmetics of the illusion of a cable-stayed bridge.
Precisely. But another aspect of this that's quite unique, if we look at it from this angle, is that the bottom element of the truss is extended out laterally so that it functions not just as the bottom chord of the truss structure, but also as the deck of the bridge, the surface on which the pedestrians will be walking. And as you can see in my model, the top chord is very much the same thing. That entire top surface functions as the structural top chord of the bridge. And this is quite unorthodox.
I mean, is this bridge unique in that respect?
In my experience, I've never seen a structure configured in this way. And that configuration poses some really significant structural challenges. There are tremendous internal forces generated in this bridge when it's subjected to its very large weight.
Right.
And those internal stresses become concentrated at the places where the top and bottom chord meet the diagonals. So those are places of particularly importance for the designer to make sure that the transfer of forces across those interfaces is done safely.
So crazy design and forces everywhere, but I guess was using concrete a factor?
That's a great question. Concrete trusses are extremely rare. Why? Because from a structural engineering perspective, one of the most important characteristics of a truss is that all the elements of the structure carry load either in tension or compression. Concrete as a structural material is really quite strong in compression, right? So this is a simulated concrete structural element. If I place it under compression, it's going to carry a tremendous amount of load before the concrete finally crushes in compression. But if I subject it to tension, it actually pulls apart quite easily.
And so what do designers or engineers have to put in place to handle those forces, to, I guess, resist them or to make them not a problem?
So what we'll see in the FIU pedestrian bridge is a technique called post-tensioning.
So what is post-tensioned concrete?
So if I had taken a steel rod and embedded it in the concrete,
Sure.
that if I wanted this element to be able to carry tension more effectively, in the case of my model where the steel rebar is a threaded rod, I might put a nut on the other end and
Okay.
then crank this nut down
So
really
you're
tight.
crushing it.
Exactly right. I'm actually compressing the concrete using the steel reinforcement. Then the entire member, both the concrete and the steel, is contributing to structural load carrying, right?
Okay.
And that's key to understanding the
Yeah.
failure, because the failure occurred as a consequence, at least in part, of this post-tensioning process.
Right. We'll get into that a bit later. So, like you say, it's unique in the use of concrete for the truss is unusual. The asymmetry is unusual, right? I mean, the way that they went about building it wasn't your run-of-the-mill construction project, I guess. So was how it was built a factor?
Yeah, so the construction method that was planned to be used is a relatively newly developed technique called ABC, accelerated bridge construction. As you recall from your picture, this is designed as a two-span bridge. There's a longer span, which was designed to pass over the 8-lane Southwest 8th Street highway. And then the shorter span on the opposite side passed over a canal. Building that second span was never going to be a problem because it's built over a canal. But this main span, if it had to be fabricated in situ, in place, would have been a major disruption to traffic.
Right. Southwest 8th might be like a suburban street there, but it's coming and going to downtown Miami and off to the rest of Florida. So like you say, you don't really want to be shutting that down for days or weeks.
Precisely. So the plan was for this span to be built on an adjoining site parallel to the road. And then, under the plan of the accelerated bridge construction paradigm, the structure would be loaded onto transporters and picked up and transported to the site.
But those transports were picking it up, I think they were about 30 feet from each end.
Right there.
Right. Now, that meant during that move, the forces were different. And so there's just one thing that they had to do there, right, whilst they were moving it to keep it all intact.
Exactly. Here's the bridge as it was set up in the yard supported primarily at its ends, in the same mode that it would be when it was put
Yeah.
in place. When the truss is in this configuration under load, these outermost diagonals are in compression. For that reason, they didn't need to be post-tensioned as far as the final configuration of the bridge is concerned.
Yeah.
However, when you pick it up with transporters from these 2 points, the truss carries load in a fundamentally different way. The outer ends are going to droop downward. And when they
Right.
droop downward, that's going to stretch the diagonals because of their orientation. Now those 2 elements are in fact in tension. For that reason, those diagonals had to be post-tensioned prior to the movement, a very unorthodox requirement that
Yeah.
was related specifically to the use of a post-tensioned reinforced concrete
Right.
truss. In 99% of all post-tension concrete construction, post-tensioning is applied and that's it. It's kept in place forever. It's never detensioned. But because of the very specific combination of this crazy truss geometry and the use of ABC construction, which would impose a fundamentally different kind of loading on the bridge during transport, the process of first post-tensioning and then detensioning was absolutely essential to the entire construction scheme. Unfortunately, it also contributed to the failure in ways that we can talk about.
Right. The first warning signs came about 3 weeks before the collapse. Starting, I think it was on February the 24th. What was the chain of events that was actually happening in the background that no one outside of the project would have known about?
Right. So the critical first event occurred while the main span was still in the fabrication yard being built. After the entire bridge had been cast, that is all 3 levels, with all the reinforcement inside, and the post-tension members were post-tensioned, the shoring was removed from beneath the span.
Right.
And at that instant, as the shoring was dropped, the bridge began carrying its own weight for the first time, and the construction workers involved in that operation heard a loud bang. And upon examination, they found significant cracking had occurred at the interface between members 11 and 12 and the deck of the bridge. What in the investigative report is called node 1112, and it has that name because on the design drawings for the truss, all of these diagonals are numbered, and this diagonal is number 11, and this is number 12. So the joint at which those 2 members come together is called node 1112.
So when they see the cracking, what would the thinking be when you see something like that? Or is it normal for concrete to crack?
The partial answer is yes, it is normal for concrete to crack. As concrete is subjected to tension, the steel stretches. You stretch the steel, the concrete is going to crack.
Okay.
There are actually standards in the design codes that say you have to design your structure such that any cracks in the concrete don't exceed, it's about 0.5 millimeter in width, right? The cracks have to be small in part to protect the steel from corrosion, right?
Got it.
But the extent of cracking in this structure at that moment was significantly worse than that 0.5 millimeter standard.
And so what did they do now?
The engineers who designed this structure were located in Tallahassee, Florida, whereas the structure is located in the Miami area.
Yeah.
And so the engineer is not on site to render a judgment about the seriousness of this event.
Yeah.
But the project managers quickly documented all the cracking. They took digital photos of it, and they emailed them to the engineer and said, well, we're seeing a lot of cracking here. What's this all about? Is this a concern? The structural engineer of record looked at the photos and determined and reported back to the project site, no concern. Cracking is normal in concrete. This is not a safety issue. The project could proceed.
Fast forward to the big move, 4 days before the collapse.
After the concrete had cured sufficiently, huge mobile transporters were used to lift the bridge off of its temporary supports and drive it out across South 8th Street. This was done in a single night. So far, so good. Apart from the initial cracking episode, everything looks fine.
And then, theoretically, it was put down, they were going to reopen the road, and they could do everything else with minimum disruption to traffic, But obviously, that's not what happened.
No, because there was no need for the post-tensioning after the bridge was in position. The plan was to detension those outermost elements. And at the moment they are detensioned, the existing cracks become significantly larger. And one of the construction workers apparently explained, it cracked like hell.
So when they see the cracking, what does everyone go, right, we've got to stop?
The construction managers recognize there's a problem, and they send a communication to Tallahassee and say, whoa, the cracking has increased significantly. This looks really serious. What should we do? The engineer reviews the photos and once again concludes that there is no safety issue, that the cracking is to be expected and can be patched up later in the project.
But in retrospect, that seems odd that given the extent of the cracking, and this isn't, I guess, trying to find fault, but it's just trying to understand, was that bad interpretation, or was it that looking at photographs doesn't convey, I don't know, I'm just trying to understand how that extent of cracking could basically be signed off.
Really, I think has to do with the psychology of being responsible for a huge complex project and then being confronted with a set of circumstances that are just completely unexpected. And his response, I think, was sort of a normal human response to assume everything was going to be okay because everything in his experience told him that his calculations were correct. And so he really just couldn't conceive of what might be causing this problem. That's purely my interpretation of the events as I read them.
Of course. We've now reached the day of the collapse. By March 15th, there was a plan to try and close them up. So is that a case of, okay, maybe someone was thinking they could be an issue, or were they just thinking, I don't think they're an issue, but also I've got an idea of how to get rid of them?
Pretty clear that the engineers did indeed have some safety concerns. They did two things. First, they scheduled a meeting on the project site for all parties involved in the project. And the second thing they directed was to retension those two critical diagonal members.
Yes.
We now have what appears to possibly be an unsafe condition. Why don't we turn back the clock? Why don't we retension those two members so we can restore the structure to the less dangerous condition it was in at the time the shoring was removed in the construction yard? Perhaps to add another margin of safety while they were figuring out how to address the problem at their on-site meeting. And the problem was, it didn't work. The logic was flawed. Because after that second round of cracking occurred, the application of additional post-tensioning force wasn't going to close up those cracks. It was only going to put more stress on the remaining intact concrete. So it was going to make the situation worse, not make the situation better. That was the straw that broke the camel's back that ultimately caused the collapse.
When you first saw the dash cam footage, what went through your mind as an engineer?
Right. So the thing I notice is that the deck folded up right at this point, right? So that drops. And there's only really one way that could happen. And that would be a loss of the structural integrity of the truss.
So that dash cam footage was crucial in helping them to see where the failure had happened.
That's absolutely true. The dash cam footage, it certainly saved time and made it a lot easier to zero in on the portion of the structure to focus upon.
Right.
In fact, when investigators examined that footage closely, they saw a small puff of dust occurring right here behind node 1112.
Although it failed because of the retention, the NTSB, as far as I can recall, they basically concluded everything else had been done according to the construction plans. I guess that's a key clue for the investigators, right?
Yeah, with regard to that particular slice of the investigation, what the NTSB investigators wanted to do was to review the design engineer's computations. They were not able to acquire that information. It's not clear why they weren't.
Right.
And so they did the next best thing. They essentially replicated the engineer's analysis work independently on their own. They created their own computer models of the bridge. They ran their structural analyses.
Ran their own numbers, basically.
Right.
So what did they find?
Here is where we see a new phenomenon, which is called shear. So when we talk about shear, we're always talking about the effect of two surfaces sliding with respect to each other.
Okay.
And in a truss structure, particularly a truss structure like this, there's a tremendous amount of shear occurring at the joints between structural elements.
I guess the question is, so why did it why had all the cracking come in the first place?
What that analysis showed was that the engineering design had erred in two different ways, both of which tended to make that critical joint, node 1112, unsafe.
Right.
They underestimated the amount of shear force that was going to be delivered to that joint as a result of the self-weight of the bridge, and they overestimated the shear strength of that connection.
So how did the bridge actually collapse?
Right. What I'm going to challenge you to do is look right here. That's where the puff of smoke emerged.
Absolutely.
At the point where the two elements connect to the deck of the bridge, and I'm going to apply load to my bridge, and I want you to watch what happens at that interface. As you can see, right there.
Right. So it pops out.
It pops out. It shouldn't do that.
No.
This joint should remain intact under the action of load. So what has happened is a shear failure has occurred around the entire perimeter of that critical node. And as a consequence, when load is applied, the joint becomes detached from the bottom cord. That loss of the structural integrity of the truss meant that this joint just kept on going. It continued to slide out. And once the strength that was provided by the connection of these members to the bottom cord was lost, it folded up right at this joint and the entire structure collapsed.
So in my sort of simplistic interpretation, the force coming down member 11 effectively pushed column 12 out. So it slid out, pushing 12 out, which took that support away, meaning that it failed at the next sort of truss connection back. So that's why it failed there.
Exactly.
So another thing that made it worse, I believe, is there were pipes in the concrete, and there's one, that's in the middle underneath the joint. So how were those, an exaggerating factor of the weakness?
Yeah, absolutely. I mean, in my model, you can see this hole right in the center of member 12 down below
Yes.
the level of the deck. That was an opening that was created for a drain pipe. That was a major point of weakness. And indeed, when the failure occurred, it occurred right around that opening. You can see it here in the model, right?
Yeah.
There were also 4 more holes that were in the deck. They're located right at the base of member 12. Okay?
Yeah.
Those were actually for post-tensioning tendons that were going to be used to support the tower when it was added, right? Those 4 holes, 2 on each side, were located exactly along the plane of weakness at the base of members 11 and 12. They too robbed a significant amount of concrete along the shear interface and therefore also significantly weakened the joint.
And one other thing that came up in the report is that there's the word redundancy, right?
Sure.
Just briefly, what does redundancy mean?
By definition, a redundant structure is one in which a localized failure of a single element, a member, or a connection does not propagate out and turn into a catastrophic collapse of the entire structural system. A structure that has multiple parallel elements, like a truss that has multiple individual planar trusses that are all structurally interconnected, is inherently redundant because one element of one truss can fail and load is redistributed throughout the structure and it stands and can then be repaired.
Right. The truss that you showed me right at the beginning has two parallel trusses, and this bridge, well, it's a single truss, I guess. The whole deck and the roof are integral structural parts of that truss system.
Right?
But somebody somewhere in the system believed that the design was redundant or had redundancy in it.
You can never argue that this thing was redundant. It might be an error in judgment because we know one single joint failed and it resulted in the catastrophic collapse of the structural system.
Okay, thank you. No, that's very clear. So basically, the collapse was all but inevitable based on what was written down in the designs.
I think that's the case, but we really also have to qualify this by saying that because of the ABC construction process, the structure was going to be subjected to a series of radically different loading conditions throughout construction. And the failure occurred as a consequence of one of those phases, and it was certainly not the set of conditions that would have been present in the completed bridge. Um, and that's a factor here because it's absolutely inevitable that a design engineer is going to put most of his attention and most of his diligence into taking care that the completed structure is designed to standard. And it's worth noting that once that second span was built out here of solid concrete, and it would have had a joint that looked like a mirror image of this, another vertical and another diagonal pointing inward, that to some extent, that large compressive force in this diagonal would have been offset by another compressive force in the adjoining diagonal. And it's very likely that this failure would never have occurred. So if the structure had just survived long enough for the construction of that second span,
The next door span.
probably wouldn't have been fatal. We would have still had the cracking, we would have still had distress, but it seems likely to me that it actually would have survived.
It might have just stood. Sort of stepping back a bit, what lessons do you feel most clearly come from this failure?
Yeah, I think perhaps from a big picture perspective, the single most important lesson is that anytime a creative, innovative design that has no precedent is attempted, a much higher level of scrutiny and due diligence is essential. And this is not to say that we should squelch innovation. This is not to say that an effort to produce a really dramatic, aesthetically beautiful bridge was a mistake. I think that creating beautiful structures is part of the obligation of the engineers because it enhances our built environment and that enhances our quality of life. But we have to recognize that the demand for due diligence is much higher when you do things that are as unprecedented as this structure.
Now, as we speak, they are in the middle of constructing the replacement bridge. I don't know if you've seen the plans.
Yes, I have. I'm really heartened that the university didn't shy away from a landmark structure
Yeah.
because of the earlier collapse. The fact that it's steel makes it less susceptible to the kinds of failures we saw with post-tension reinforced concrete. It has a somewhat higher level of redundancy. So it is a safer design in many respects. It's really wonderful to see that a signature structure is going to cross Southwest 8th Street at that location after all.
Excellent. Very clear, thank you.
Sure. Thanks, Tom. And it's a pleasure to be part of this project.
Once again, a huge thanks to Dr. Steve Ressler for taking the time to talk to me about this tragedy, and to you for watching. If there's a story you'd like to know more about, add it in the comments and I'll look into it. Meantime, any likes or shares would be hugely appreciated. And look out for more stories coming your way on Why Stuff Fails. And for anyone who's still watching, these are edited down from much longer, more detailed conversations of around 90 minutes. If there's an appetite to see those in full, let us know and we'll find time to post those too. And that is it from me. Thanks again for watching.